Hello everyone. In the previous class, we have discussed about what? The specific heat, molar specific heat, and what? Heat capacity. So heat capacity is called specific heat, and molar heat capacity is there. So two types of concepts we discussed in previous class: degrees of freedom, and what? The specific heat capacity, and degrees of freedom. And next important topic is that liquefaction of gases. What is that? Liquefaction of the gases. So in this liquefaction of the gases, what we are going to study is that how gas can be converted into liquid. How gas can be converted into liquid. That means if you want to convert the gas into liquid, first what we have to do? First thing what we have to do is we have to cool the gas. We have to cool the gas. Okay, to critical temperature. To what here? Critical temperature. So we have to cool the given gas to the temperature below critical temperature. Below this critical temperature only gas can be liquefied. So below critical temperature of the gas only it can be liquefied. So below TC only, below critical temperature only, gas can be liquefied. So gas can be liquefied only below what? Critical temperature. So that point we have to first understand. So we have to cool the given gas. We have to cool the given gas to what? The critical temperature. And below this critical temperature only we can convert the gas into liquid. That's first thing. After reaching this critical temperature, we have to apply pressure on this gas. So we have to apply what now here? Pressure on the gas. So we have to apply pressure on the gas. So when you apply pressure on the gas, what happens now at the critical temperature? It can be easily converted to liquid. The gas can be easily converted to liquid by cooling the gas to the temperature below critical temperature, and then we have to apply what? Pressure on it. We have to apply pressure on that. So these two things we have to do first. So first thing what we have to do is what now? Cool the gas to the critical temperature. After that, we have to apply the pressure on the gas. So the gas will be converted to liquid. This point keep in mind first. Now, first point, a gas may be liquefied by cooling or by the application of high pressure, or sometimes by the combined effects of both. Here, what we have to understand is that one point. Now, if you apply high pressure on the gas directly above this critical temperature, if you apply high pressure on the gas also, it will not be converted to liquid. The gas can never be converted to liquid if you apply high pressure on the gas above the critical temperature. Remember, only below critical temperature we can liquefy the given gas. That point keep in mind. And that critical temperature will be different for different gases. For different gases, critical temperature is different. That point keep in mind. So first we have to cool the gas to below critical temperature. After that, we have to apply high pressure. Next, the first successful attempt for liquefying gases was made by whom? Van der Waal. So sorry, Faraday. Faraday has given what now here? Faraday has liquefied the gas for the first time. Van der Waal explained what? The real gas behavior. Okay. Next, so the gases for which the intermolecular forces of attraction are small, such as what? Hydrogen molecules, nitrogen molecules, argon, oxygen. For these here, the intermolecular attractions will be somewhat lesser. So here, least will be here. So in the given list now, here in the given list, least will be what now here? Least intermolecular attractions will be H2. So least value of A. A is what? Magnitude of intermolecular attractions. Now? The Van der Waals constant A indicates what? The magnitude of intermolecular forces of attraction. So the intermolecular force of attraction will be less in case of what? In case of this, what here, hydrogen in the given list. In the given list, it is less for hydrogen gas. And next one, yeah, these what here molecules in which the gases in which the intermolecular attractions are somewhat lesser, smaller, have these molecules have low values of critical temperature. Remember, So low values of critical temperature. The critical temperature formula what ma? Tc is equal to critical temperature. So I told you three types of temperatures now. CBI, CBI, CBI. In that critical temperature will be what now? 8A by 27 RB. 8A by 27 RB. It is what now here? Critical temperature. A by RB generally 8 by 27 into A by RB. So 8A by 27 RB is what critical temperature. How critical temperature and this A value related here directly proportional. The critical temperature of a given gas is directly proportional to its A value. A is what magnitude of attractive forces. If attractive forces are less, critical temperature will be less. If attractive forces are less, critical temperature will be less. That point keep in mind. Okay, ma? Next. So these have what now? These gases have less Tc value and cannot be liquefied by the application of pressure. Cannot be liquefied by the application of pressure are known as what? Permanent gases. The gases which are having lower value of small a, that means lesser attractive forces between the gas molecules, which are having low critical temperature, are called what generally? Permanent gases. The permanent gases examples what you can write: hydrogen gas, nitrogen gas, argon gas, and oxygen gas. These gases are what now? Permanent gases. These permanent gases have what? Tell me. These permanent gases have smaller values of what? Smaller A, smaller Tc. A is smaller indicates what now here? Attractive forces are less. Force of attraction will be less. So smaller forces of attraction. So forces of attraction will be less. Tc, critical temperature will be less, and A value will be less for these gases. So they are permanent gases, we say. So tell me examples for the permanent gases now. Hydrogen, helium also you can take. Hydrogen, helium, neon, argon, oxygen. So helium also you can take. So these gases are permanent gases, we say. So mostly they try to remain permanently as what? Gases. They don't want to be converted into liquid. That's why they are called, they are given the name what? Permanent gases. But still we can convert the nitrogen into liquid, oxygen into liquid, argon into liquid. But hydrogen, it is difficult to convert into liquid state. To convert the hydrogen gas into liquid state, it is somewhat difficult, remember. Okay. Next one. While the gases for which the intermolecular attractive forces are large, the intermolecular force of attraction are large between the gas molecules, such as what? Polar molecules. Polar molecules like NH3, SO2, and H2O, ammonia, sulfur dioxide, and water. These molecules are polar molecules, and the hydrogen, nitrogen, argon, oxygen are what? Non-polar molecules. Each molecule is made up of same atoms, na? Similar atoms. That's why these are called non-polar molecules. And see, NH3 molecule is made up of two different two different types of elements, hydrogen and nitrogen. Now there is electronegativity difference between nitrogen and hydrogen. That's why this molecule must be called what? Polar molecule. SO2 is polar molecule. H2O is polar molecule. So the molecules which are having large attractive forces, such as polar molecules, ammonia, sulfur dioxide, and H2O, have high values of Tc. They are having what? Higher values of Tc. So greater the intermolecular force are large, meaning what? Greater A value. Greater A value. The magnitude of attractive force is greater here. That's why Tc will be higher and can be liquefied easily. These gases can be liquefied easily. Ammonia can be easily converted to liquid state because it has what? Higher value of Tc. Higher value of Tc. So liquefaction process and Tc value, how they are related now? If Tc value is higher, okay, what will be easy? The liquefaction will be easy. So the process of liquefaction will be directly proportional to what? Critical temperature. So more the critical temperature, more easily the gas can be converted. That point you can keep it mind here. So the liquefaction. So liquefaction of gases, liquefaction of what? Gases is directly proportional to or inversely proportional? Directly proportional to Tc. more the TC value, more the critical temperature value, more easily the gas can be converted to liquid state. That point keep in mind. Okay, and also directly proportional to what? A value. A is what? Magnitude of attractive force. More the magnitude of attractive force between the gas molecules, greater will be TC value. Then what will be greater here? Liquefaction will be easier. It will be done easily. Okay. Next, methods of liquefaction of gases. So, by which methods the gases can be converted to liquids? That is liquefaction. See here, the modern methods of cooling the gas, the modern methods of cooling the gas to or below their critical temperature, and hence of liquefaction of gases are done by Linde's method. What is the method here? Linde's method and Claude's method. By two methods, we can convert the gases into liquids. Remember here. What are the two methods here? What are the two methods? One is what? Linde's method. One is Claude's method. Just a moment, ma. Okay, ma. So the first method is what here? Linde's method here. What is this method, ma? Linde's method of liquefaction of the gases. Okay. So this process is based upon Joule-Thomson effect. What is the method here? So the Linde's method is based on which effect, ma? Joule-Thomson effect, which states that when a gas is allowed to expand adiabatically, when a gas is allowed to expand adiabatically from a region of high pressure to a region of extremely low pressure. So when a gas is expanding, when a gas is being expanded and it is allowed to pass through the high pressure region to low pressure region, it is accompanied by cooling. It is associated by cooling, associated with cooling here. So what they are saying is that in this method, suppose gas is taken at high pressure. Initially, gas is taken at what, ma? High pressure. At high pressure, we have taken some gas. Remember, this gas at high pressure is allowed to pass through what? Pass through what? Gas at low pressure. Low pressure means extremely low pressure, very low pressure. So very low pressure we have taken. Very low pressure is obtained from high pressure. The same gas. Now same gas is taken to low pressure. Okay, the gas at high pressure is taken to low pressure, and here expansion is going on. Remember, what is going on? Expansion, not the contraction. Expansion is going on. So when gas is expanded from high pressure to low pressure, very low pressure, okay, it will be associated with what? Cooling or heating? It will be associated with cooling. And this expansion should be what here? Which type of expansion? Adiabatic expansion. What is this called, ma? Adiabatic expansion. So adiabatic expansion we say. So adiabatic expansion will be used here. So by this adiabatic expansion, the gas at high pressure is taken to gas at low pressure, and it is showing which effect now here? Cooling effect. Cooling effect. The gas exhibits what? Shows what? Cooling effect. And this effect is called what now? Joule-Thomson effect. So Joule-Thomson effect is nothing but when a gas is allowed to expand adiabatically from a region of high pressure to a region of extremely low pressure, the gas is accompanied by cooling. The gas is associated with cooling. The point keep in mind. Now what we have to understand is that adiabatically, the word adiabatically. Adiabatically meaning what here? The heat transfer is zero. The heat transfer does not take place. That means what now here? The heat is not transferred from the system to surrounding or from surrounding to system. A system is gas. We are observing what now? The property of a gas. Na? The gas is neither losing heat nor gaining heat. That is called what now here? Adiabatic. So adiabatic condition meaning what? Delta Q. Delta Q is zero. Delta Q means Q indicates what? Heat here. The heat. That delta Q means what? Final heat minus initial heat will be same. Okay, the initial heat and final heat will be same. The delta Q is nothing but what? Q2 minus Q1. That means final heat of the gas minus initial heat of the gas will remain constant. That means what now? What we have to understand? The heat changes are not taking place. When heat changes are not taking place and the gas is expanded, that expansion of gas is called adiabatic expansion. You have to understand. So adiabatic expansion you have to read. And one more thing you have to understand here. Some words in chemistry, in science, we have to understand like this here. Suppose you take here I and A. Both are what? Both are what? Vowels. When two vowels are there, first vowel we have to read, okay, in native language, native pronunciation. That means what? ADI, adi, we have to say. Don't say adiabatic. Adiabatic wrong. Adiabatic we have to say. Here, first vowel only we have to. Second vowel we should be taking as silent. It is not what read. A should not be read. So adiabatic expansion we have to say here. Is that clear, ma? So adiabatic expansion is nothing but the expansion of the gas when the heat changes are not taking place. That point we have to understand. So allowed to expand adiabatically from a region of high pressure to a region of extremely low pressure. It is accompanied by what? Cooling here. Is that clear, ma? It is the Linde's method. Next one is what now? Claude's method. What is that, ma? Claude's method. This process is based upon the principle that when a gas expands adiabatically against an external pressure, when a gas expands adiabatically against what? An external pressure, it does some external work. The gas will do some external work. The gas does what? The gas does some external work. Okay, so once again, see this process, Claude's process is based upon the principle that when a gas expands, diabatically against an external pressure, some external pressure is there on the gas. Against the external pressure, the gas is trying to expand, suppose, expand. So what is given example here as a piston in an engine, in car engine, in machine engine, okay, there will be piston moving up and down. The piston is moving up when gas is doing some work. When liquid is doing some work, the piston will move upwards. When piston is moving downwards onto the liquid, the piston is doing work on the gas, on the liquid. When piston is moving up, what we have to understand? The liquid or gas is expanding and doing some work on the piston. Like that we have to understand. So simply remember that when gas is expanding, if gas expands, what does it mean here? Work is done by gas. Work is done by the gas. Okay, work is done by the gas when we say if gas is expanding. Suppose if the gas contracts, what we have to say? The work is done. The work is done on the gas. Work is done on the gas means what here? The gas contracting. Gas expanding means what we have to take? Work is done by the gas. So here the gas is doing some external work here. The gas is doing some external work. Means what? Expansion or contraction? Expansion is going on. Which type of expansion we are taking? Adiabatic expansion we are taking. Heat changes will be 0. Delta Q will be 0. No heat is transferred from the gas to surrounding or surrounding to gas. Okay. So in this condition, the gas does some external work. Since work is done by the gas molecules, since work is done by the gas molecules at the cost of what? Their kinetic energy. Already gas molecules are having what? Kinetic energy now. So this kinetic energy will be utilized to do some work. Some amount of kinetic energy will be utilized to do what? Some work. Okay, therefore, what happens now here? Some kinetic energy is used up here. That means the quantity of energy, the amount of energy decreased. That's why what happens? The temperature of the gas falls. Falls means what? Decreases. The temperature of gas decreases, causing cooling effect. Causing which effect? Cooling effect. The cooling effect will be caused by the fall of temperature, by the decrease of temperature. Why temperature is decreased? Why temperature of gas is decreased here? Because some amount of kinetic energy of gas molecules is used to do some external work. To do some external work. Is that clear, ma? That's why this concept is to be understood very clearly. This expansion of gases and contraction of gases, work done by the gas, work done on the gas, all these things you will study in thermodynamics chapter. The thermodynamics, thermochemistry, one chapter is there. We are going to discuss that topic. Okay, then you'll understand what now. This important area of this one. Okay, so just a moment, ma, 1 minute. I will charge this. Just a moment. Yeah, okay, ma. So here now what we have understood here, this expansion of gases, contraction of gases, we'll study in what? Which topic? Thermodynamics and thermochemistry. That lesson is there. Next now, by another is what now? By adiabatic demagnetization. So here we used what now? Two methods now. First method is what now here? First method is Linde's method. First method is Linde's method. Second method is what? Second method is Clark's method. Okay. And third one is what? By adiabatic demagnetization. D means removal of magnetic properties. If any magnetic properties are there for the gas, if gas has some magnetic properties, by demagnetization, adiabatically means what? Delta Q will be 0. Okay, D means always removal. If magnetic behavior is removed, if magnetic behavior is lost, if magnetic behavior is removed, that is called what? No, demagnetization process. And adiabatic means what? The heat changes will be not taking place. Gas to surrounding to gas, the heat changes will not be taking place. Heat transfer does not occur. That is called the adiabatic condition. So by adiabatic demagnetization also we can cool the gases. Okay, so the liquefaction of gases in three methods we understood. Next one, uses of liquefied gases. Now, what is the use of liquefaction of gases? Why we are converting gas into liquid? So, because there are uses, there are some uses of what? Liquefied gases. Examples here. So, liquefied and gases, okay, compressed under a high pressure are of great importance in industries. So the liquefied gases are which are compressed under high pressure. Liquefied gases which are compressed under a high pressure are of great importance in industries. In industries, they are having great importance. Remember, which one? These liquefied gases under high pressure. Okay. Now, first one, liquid ammonia. So the liquid ammonia and liquid sulfur dioxide, liquid ammonia, okay, are used as refrigerants. Refrigerants meaning what? Coolants. They will cool. They will be used to give what now here? Cooling effect. So cooling effect will be done. Cooling effect will be done by these gases. Liquid ammonia and liquid sulfur dioxide are used as what? Refrigerant. Okay. Next, liquid carbon dioxide finds use in soda fountains. Okay, for attraction, soda fountains will be there, not the fountain by water. Soda fountains will be there. So in the liquid fountains, what will be used? Liquid carbon dioxide will be used. Next, liquid chlorine gas, liquid chlorine, liquid Cl2. Here, liquid CO2. Okay, liquid Cl2 is used for bleaching and disinfectant purposes, to disinfect the substances and to bleach the substances. We use what now here? Liquid chlorine. So liquid chlorine is used for bleaching purpose and disinfectant purpose. Disinfectant purpose meaning what here? For disinfecting means to kill the germs. To kill the germs, we use this one. That's why chlorine will be added to what? Well water to kill the bacteria in the well water. Okay. Next, liquid air also gas now here. The liquid air is an important source of oxygen. So if you want to get liquid oxygen, we get it from liquid air in rockets and jet propelled planes and bombs. So in bombs, in jet propelled planes and in rockets, we use what now here? Liquid oxygen. So liquid oxygen will be used, which is obtained from liquid air, remember. Okay. Next, compressed oxygen gas. Compressed oxygen gas is used for welding purposes. For welding the heavy metal blocks, we use what now here? The liquid oxygen. Okay. Next, compressed helium means liquid helium. Actually, here liquid helium we cannot say because the helium cannot be liquefied easily. Helium cannot be, helium gas cannot be liquefied easily. It cannot be liquefied easily. So as it cannot be liquefied easily, okay, we have to say compressed helium here. We should not say what here, liquid generally. So compressed helium is used in airships. In airships, what we use here? Compressed helium gas. Okay. Next, Joule-Thomson effect. Another important topic is what? Joule-Thomson effect. Okay. So when here also you see what I said, the one principle for reading the names of scientists and some terms. Here, when two ovals are side by side, first oval only we have to read. Second oval will become silent. So Joule we have to say. Don't say joule, joule, Joule. Okay. So Joule-Thomson effect. So when a real gas is allowed to expand adiabatically, here again which expansion is taken? Adiabatic expansion. Adiabatic expansion meaning what I told you? Delta Q will be 0. The heat transfer will not take place. So allowed, when real gas is allowed to expand adiabatically through a porous plug. Through a porous plug means small hole, very small hole. So small hole when you allow the gas to expand suddenly, or a fine hole they said here. So porous plug is nothing but fine hole is called aperture. What is this called? Aperture. Aperture or fine hole or porous plug. Through this small hole, when you allow the gas, when you allow the gas to expand adiabatically, into which region? Into a region of low pressure. From high pressure to low pressure, we are allowing gas to flow. The gas is flowing from higher pressure region to lower pressure region. The gas is accompanied by cooling. Accompanied by cooling means associated with cooling effect. So except for hydrogen and helium, which get warmed up, means heated up. They will be heated up. So these two gases will be heated up, but the remaining gases will be giving cooling effect. So under what condition here? If a gas is expanded adiabatically from higher pressure region to lower pressure region, it will exhibit cooling effect. It will show cooling effect. So this is what we have to understand. This effect is called Joule-Thomson effect. Okay. Next one, see. Cooling takes place because some work is done. Some work is done by the gas here. Remember, the work is done by the gas to overcome what? The intermolecular, to overcome the intermolecular forces of attraction. To overcome the intermolecular attractions, some work is done here. Some work is done. Okay. So as a result, the internal energy of the gas decreases. Internal energy of the gas means capital E, otherwise capital U we use here. Internal energy, U, otherwise E. So these all things we'll study in thermodynamics. Just to get the words into mind first. The internal energy of the gas meaning what? The total energy of the gas. The gas will contain what? The gas molecules have what? Kinetic energy, potential energy, vibrational energy, rotational energy, and many forms of energies. The sum of all the forms of energies of gas molecules will be together called internal energy. So now what happens now? The internal energy decreases and so does the temperature. That means what now? Temperature also decreases, meaning temperature decreases as well as internal energy decreases. Why temperature is falling here? Why temperature is decreasing? Because some work is done by the gas. Some work is done by the gas to overcome what? The intermolecular forces of attraction. Because of that, what is decreasing here? Internal energy is decreasing. Internal energy is decreasing for the gas, and also temperature of the gas is fallen. Temperature of gas is decreased here. Is that clear, man? So because of this, cooling effect will be occurring here. So last point, listen to this. After that, we'll stop. Ideal gases do not show. Ideal gases do not show any cooling or heating effect. You see, the hydrogen type of gases showing heating effect, and other types of gases showing cooling effect. But ideal gases Ideal gases are what now? Do not actually the gases which do not exist in the nature are ideal gases. Ideal gas is what? Hypothetical, imaginary. No gas is ideal actually. But if you imagine ideal gases do not show any cooling effect or heating effect because there are no intermolecular forces of attraction. There are no forces of attraction between gas molecules. So here what we said, reason for real gases to overcome the intermolecular forces. Some work is done, we said. But here no work will be done to overcome intermolecular forces because the intermolecular forces of attraction only not there. There are no intermolecular attractive forces between gas molecules of ideal gas. That is, they do not show Joule-Thomson effect. Ideal gases do not show. Ideal gases do not show what? Joule-Thomson effect. They do not show cooling effect or heating effect. Okay, so the remaining points we'll discuss in the next class now. Okay, bye, good day, take care.